And if you please can mute from your side. So what we said that the tube-to-tube sheet joint will be identified in the data sheet, mean that it is part of the thermal design of the heat exchanger. That's why in next step where the mechanical engineer will be more involved, he should pay more attention to the type of the tube-to-tube sheet joint selected or identified. There is many factors in the material need to be considered, which we can ideally don't assume that the process engineer or the thermal design engineer is that much aware of it. Now for the different types of the tube-to-tube sheet joints, there is no one selection suits all the application, either from the application perspective to have the proper design or the proper characteristic of the joint, or even from the cost perspective. That's why you need to think about the proper joint to be used for each case. Each type of joint has its own strength and weakness, so you need to balance the features for each joint and then to select or apply the proper one for your application. Now for the expanded only, it is the most economical one. There is no welding associated with this, and it is easier to be retube in the future. So if you are looking in the future maintenance or repair, it is much easier to remove the expansion and remove the tube and reinsert again, other than removing welding and again re-weld. Future plugging with the expanded only, you can easily use the tupper plug, which is very simple to be applied. And there is no tube sheet beveling required, means the machining of the tube sheet face is not required, so it's also much less work activity required. But in the weaknesses, can be loosened over time, especially under the cyclic load or maybe the temperature or the high differential pressure between the two sides. And in some cases, it is potential to stress corrosion cracking if you have that much high residual stresses in the application. That's why some material, we will see later, that you have to limit the application to what extent it will be expanded. And it is somehow not something strange, like there is frequently reporting that the proper parameters need to be maintained during the application of the expansion somehow is misunderstood, which led in some cases to the frequent leaking or issue than the heat exchanger. So it looks simple, but somehow there is some it has its own experience and technical requirements, and it's highly sensible to the axial scratches, because the tube, once you expand it with the tube sheet, it will take the shape of the tube sheet hole, including the imperfections and scratches. Expanded and seal welded, it is much better compared to the expanded only. And you will have more leak resistance and sealing for the leak. So it is somehow much preferred compared to the expansion whenever you have a little bit higher critical service, where there is no tolerance accepted to have a mix between the two sides. The weaknesses for this one, you can consider that the small weld size still somehow vulnerable to be leaking in case there is some issue in the joint. Retubing in the future, you will need to do welding, so some more work is required. And in case post-weld heat treatment is required, especially for service-wise, so it will be something of some interest during the initial construction. And the main concern here will be during the plugging or retubing. To do post-weld heat treatment at site, it is not an easy application to have, you can say, uniform application of the post-weld heat treatment. And also the limitation of the inspection technique for the weld, and this will be a common somehow limitation for all the weld joints. Strength and welded, but not expanded. You can apply only strength welded without expansion. The weld size calculated to be strong enough, as we will see in the requirement of the ASME, and there is no expansion groove needed for such a type of joint. So somehow less machining is required and less work, and there is no expansion also, so this step will be eliminated. But it is potential to crevice corrosion, because the backside of the weld will have a gap where the fluid or from the shell side can accumulate and cause crevice corrosion. And also the limitation on the inspection technique, which we said it is applicable for all the welding joint type. Retubing in future will be something required. Removing the weld, somehow conditioning again of the bevel of the tube sheet, and re-weld again, And if you have post-weld heat treatment required, it's also not an easy application, especially during the repair in future or retubing. Future plugging cannot be only taper plug. You have to either install mechanical plugs or the welded plugs. And under cyclic load, in case you don't have the expansion, this strength weld will be subjected to fatigue cracking, and it might be cracked. The last type, or the last, let's say, configuration, maybe strength weld plus expanded, and this is the most leak resistant one. You will have the strong weld, and you will have also the expansion, which will close the gap. You will eliminate the to a very good extent the susceptibility to crevice corrosion, and the weaknesses part will be, it is a little bit the more intensive work, so it is somehow from cost wise the higher cost, and the limitation on the inspection, as we said earlier. And again, all the requirements for the welding here, for the future plugging, post-heat treatment if required, where you need to remove the weld or apply again weld, or the application of the post-heat treatment at site, which is a very challenging exercise. In high temperature surfaces, usually, or aggressive load, usually you cannot rely only on expansion. You need to have welding, whether you can apply strength weld plus seal plus light expansion, or expanded plus seal weld. Now for the requirement of the tube-to-tube sheet joint, the percent of the expansion. The percent of the expansion recommended depend on the material will be used. Some materials are subjected to work hardening, or some other material might go for the residual stresses in future, might cause stress corrosion cracking in service. That's why the percent of application of the wall reduction, how much it will be expanded, depend on the material. We will see the ductile material like carbon steel or low alloy steel, you can apply up to 8%. And between the two common standards in the industry you are using, TEMA, Tubular Exchanger Manufacturer Association, or the API 660, the standard of shell and tube heat exchanger, there is some minor variation in the recommendation, but almost it have the same approach or the same trending on the recommended percent of expansion. What we can see here, that for the duplex stainless steel, for the austenitic stainless steel, you have a little bit less recommended target wall reduction or expansion, while for the copper alloys and also for the carbon steel or low alloy steel, you can apply a higher degree of expansion without any issue. For the duplex stainless steel, we can see in API 938C, for the use of duplex stainless steel, somehow they are recommending light expansion up to 2% only, plus strength weld, means you cannot apply only the expansion. But again, this is a technical report. This is a good engineering practice. We saw for some application that up to 5 and 6% applied in duplex stainless steel in many cases. Now, one factor also have a contribution on how the tube will be affected under the expansion is how much gap or clearance between the outside diameter of the tube and the tube hole. In TEMA, there is standard fit clearance or special fit clearance, and it is highly recommended to have the special fit clearance, the special close fit clearance, where there is minor or small gap between the tube and tube sheet hole, so that you will don't have more plastic deformation in the tube while applying the expansion. Against this one, the standard fit with higher clearance, it is in many cases preferred by the manufacturer because it facilitates the insertion of the tubes during the fabrication work itself. But as far you don't have the limitation on the material, you can apply standard fit. But the best recommended practice is to apply the special close fit. And here, especially for the austenitic stainless steel, duplex stainless steel, titanium tubes, you need to apply the special close fit clearance. For the preparation of the tube sheet hole shall be clean, and there is no specific requirements to be like a polished, well machined hole, because somehow you need to have a force to grab the tube to the tube sheet hole. But it's very important to avoid any scratches or imperfections in the tubes. And this is as a general rule, it should not be there, but also we need to understand that the longitudinal imperfection is considered of higher risk compared to the radial imperfection. Now, if this is the shell side and the other one is the tube side, means the longitudinal imperfection, you will have a leak pass between the two sides. This one somehow still, it's not a leak pass, so you can have some tolerance in the radial imperfection. But generally, you should not have any imperfections or scratches in the tube sheet hole. When you're applying the two different techniques normally used in the expansion, whether the mechanical rolling or the hydraulic expansion, as we'll see next slide, the hydraulic expansion will force the tube to take exactly the shape of the tube sheet hole, including any imperfections or scratches you will left in the tube hole. That's why it is very crucial, and you have to make it well machined to avoid such impact on the tubes, which might lead to whether impacting the tube in future for some cracking or something like that, or to have a leak pass between the tube side and shell side. The three different techniques normally used is in the expansion is the roller expansion, hydraulic expansion, and it's explosive expansion. Normally, when we need to apply the expansion, you should have an annular ring grooves. And these ring grooves, the most common is to have two grooves as per the TEMA requirement, but there is some exception in case you have a thin tube sheet, which thickness is less than 1 inch, you can apply only one groove. For the roller expansion, against the hydraulic expansion, there is a different recommendation in the recommended width of the groove itself. In the roller expansion, it is fixed value like 3.2 mm, while in the hydraulic expansion, it is a function of the tube mean radius and the tube thickness. We will see here this exercise in this table. We make a comparison in case for some different tubes with different thicknesses, how much the width of the groove might be required for whether mechanical roller or hydraulic expansion. You will see a major difference for the recommended hydraulic expansion. By experience of some of the manufacturer, yes, there is a very it is very important to maintain such kind of a little bit higher width of the hydraulic expansion to maintain or to have the proper sealing of the hydraulic expansion. Especially in the hydraulic expansion, the tube will take the shape of the groove because you will apply a pressure here, as we'll see. So if the groove is that much, the width is very slow, is very small, the tube will be forced to take this shape, and it will have a localized high expansion, which might have stress concentration on the edge of the tube at the edge of the groove, and in future it might lead to some cracking or stress corrosion cracking for some surfaces. This is the application of the mechanical roller. In the mechanical roller, we can see different tools and different types of the mechanical roller, and there is different manufacturers working on that. But you need to understand also, and this field, it has its own specialty. In many cases, you need to consult also the manufacturer of the tool. There is some good recommendation well known by the experiments and experience only for the roller application, how much pressure to be applied, whether to be in one step or in a stepwise application of the tube sheet, how much rollers is required, like what we can see here for the thin tubes, 3 to 5 rollers should be applied. And also you need to think about the ligaments and the ligament between the tube holes. Somehow it is different between the triangular. We have 4 types of tube pattern: triangular, rotated triangular, square, or rotated square. In the rotated square and the square, you will find a little bit more material in the, this is a ligament, but in the area of the ligament, you can say there is more material from the tube sheet as compared to the rotated triangular and triangular, mean that under the same force or the maximum force, which can cause some deformation in the hole itself, in the case of triangular will be less compared to the square or rotated square, assuming the same material of tube sheet and same thickness as well. So that need to be considered. This example of a roller with three rolls, and there is 2 rolls, and in some tools 5 rolls, like what is usually recommended for thin tubes, like the examples of titanium tubes, where normally we can use 0.6 up to 0.8 or maximum 0.9 mm thickness of the tubes. You have to apply 5 rolls in this case, otherwise you will face some issues on cracking in the tube itself. The hydraulic expansion, the application of the hydraulic expansion is by applying hydraulic pressure in a tool inserted in the tube sheet in the area of the tube sheet hole, and by applying the pressure you will force the tube to seal against the tube sheet hole. And this application, as we said, it might apply without groove in some cases or with grooves. And in the hydraulic expansion, the uniform application of the pressure will force the tube to take exactly the shape. So if you have groove, it will take exactly the shape of the groove. This is not usually the case of the mechanical rollers, because the mechanical roll will have a little bit longer length, so the groove will come somehow in an area within the roll. So the roll have a maximum OD. It cannot go beyond the maximum OD of the roll itself. But in the hydraulic expansion, it is a pressure, so the pressure will force the tube to go and somehow do more plastic deformation in the groove. That's why the width of the groove in the hydraulic expansion need to be well respected, like the recommendation in the team and the manufacturer. It has a little bit wider width. Now we'll come to the whenever we are applying welding for the tube-to-tube sheet joint. Welding can be whether manually or by automatic welding, by the orbital welding techniques, and usually applying with the gas tungsten arc welding. It is highly recommended to have as a minimum of 2 weld passes. 2 weld passes, and this recommendation you will find in many standards, including the API 660. 2 weld passes as a minimum, and might be more. So you also, in the selection of the filler wire, you have to respect achieving this one during the application of the qualification of the WPS. One of the challenges while doing the welding of the tube-to-tube sheet joint is the relative high thickness of the tube sheet. Will you have high heat sink, and will cause high reduction in the temperature during the application of the weld. That's why in the material where you need to maintain interpass temperature to avoid any issues, like what's the recommendation for some materials. In such cases, you might need to apply preheat, and this application of the preheat should have been applied uniformly on the tube sheet. Otherwise, you might have an issue in the ligaments area in some thin tube sheets. And this will be a very big challenge if you are working in the after service for repair or doing some activities in the tube sheet. The control during the workshop in the initial manufacture or fabrication, somehow it can be better monitored and controlled for the application. But like what we'll see later, how you need to think about the future work in the heat exchanger during the design. Those are some of the common or accepted configuration of the tube-to-tube sheet joint. To the right here, we will see this is from ASME Section 8, Division 1, UW20. These are some of the recommended shapes of the or configurations of the welded tube-to-tube sheet joint, whether by fillet weld or by groove, or like this one, or by combination between groove and fillet weld, whether equal size or different size. But other than those recommended in ASME, and you are not restricted to use only the ASME configurations, there is some other configurations like what you can see here, different configuration, or like this one, would you have some setback tube to tube sheet weld, where it is welded to the back side of the tube to avoid any crevices at between the tube and the tube sheet hole. Or the one of the common recommendation, instead of the normal V groove, to apply J groove. J groove, if you can see here, or U groove, if you can see, compared to the normal V groove, you have better chance to have full penetration of the root pass compared to the V groove, especially for such small sizes of joints. And there is much limitation known for the inspection of the tube of this weld joint, especially at the root pass. So in this case, it is highly advised, and in some specifications of some well-known companies in the industry, they are recommending only using the J groove because of this reason. In some other applications, you might apply the tube-to-tube sheet joint to a cladded or welded or weld overlay face of the tube sheet. And in some other cases, it is highly advised not to do expansion like what we can see here, only welding, and we will see later why this recommendation is advised. Those are some of the special TTS welding configuration we can see in the industry. It's not listed in ASME, but it is somehow will use in many applications. This one is a special setback weld. We can see normally in the weld of the waste heat boilers in the reformed section of ammonia, methanol, and hydrogen plants, where there is some, you can say, small lip in the tube sheet from the shell side. And the tube also has a lip like this, like a step. And while welding, it will be fused together. So you will totally fuse this part, and you will not have any space or any clearance where you can have a chance for crevice corrosion. And this is highly recommended for this service because temperature here is too much high. And in the shell side, there is boiler feed water. Even with minor contamination of the salts in the boiler feed water, you might have the crevice corrosion here of much high risk. And this internal bore welding, where the tube actually is not inserted to the tube sheet, but it is butt weld to the back side of the tube sheet. And this application called internal bore weld. This butt weld have many advantages. Like you cannot have you will not have the crevice here between the tube and tube sheet, and you will also can apply the proper inspection using digital RT or UT in for the weld joints. So you will have very good confidence in the quality of the applied weld as well. And this welding joint, this is one of the special recommendation where there is some cladding material of special alloy here, and the tube also with the same material, while the tube sheet is carbon steel. And in this one, the welding between the tube to the tube sheet face, the cladded surface, and it is highly recommended to avoid doing the expansion. And if you can remember from what we said in our earlier slides, that it is highly advised to do the expansion to close the crevice. But in this case, it is the opposite recommendation. Why? Because in the tube side here, the fluid, this one is usually you can see in the carbamate service in urea plants. The media here is carbamate, which is highly aggressive to the carbon steel. So in case there is some issue in the tube to tube sheet joint, and some of the carbamate media will pass from here, in case you have a good expansion, so you will have a restriction in the flow. This carbamate is highly aggressive to carbon steel, and you will see a case history at the end where you will see very big cavity in the tube sheet because of that. But while you don't have expansion here, you have a gap, means once you have an issue in the tube, the leak will pass easily to the shell side, and the parameters monitored of the shell side from the conductivity, ammonia traces, or whatever might come from the tube side to shell side, you can easily detect. Then you can take the proper action, usually by isolating the unit and shut down the plant to take the action before having an aggressive attack to the tube sheet. Now we will have a look how the ASME Section 8 Division 1 is calculating the required thickness or throat for the different weld joint of the tube to tube sheet. As we said earlier, there is two types of the strength weld, full strength weld, partial strength weld, and also, if you can remember, the seal weld. But for seal weld, there is no calculation required. It is only a supplementary requirement for the sealant by the expansion, so no calculation required. But for the full strength and partial strength weld, there is some equations need to be applied where you can calculate the minimum dimension of the weld required. And if you can see here, the recommendation for the full strength weld compared to the partial strength weld, the full strength weld is more stringent, as you can see. Here it is whether the greater of AR calculated from the equation or up 1.40, while for the partial strength weld it should be greater only from AR. You will see the same for the different configuration. So if you can have like a fast look here as initial understanding, you will see like the AF, the weld size or the weld leg here, it should be greater than AR. Or 1.40 means under any condition this AF should not be less than 1.4 from the tube thickness. It might be higher, but it should not be less than this one. While in the groove, T is acceptable up to T in case the AR is less than the thickness. We will have later an example for how to calculate it when we'll talk about the minimum leak pass. Now for the welded and expanded. There is a very famous question asked many times when we have the configuration between expansion and the welding, both are applied. What we have to do? Expand first, then do the welding, or weld first, then do the expansion. There is no one answer will say yes, this is a highly recommended one, but you need to understand the pros and cons for each of those applications, so you might select the most proper one or the most proper choice for your case. If you are doing the expansion first, then the welding means the expansion will close the gap between the tube and the tube sheet hole. So in this case, while applying the weld, you will close the gap where the weld gases should escape. So you might have higher chance for having weld porosity, especially in the root pass of the weld. Also, the welding after the expansion, the heat from the weld and maybe from the heat post-weld treatment also, if it is required, it will do some loosening for the expansion. So whatever the expansion you have done earlier will not be the same intact like after applying the welding. And also one of the features in the expansion then welding, that doing the expansion first, so you might do some testing like leak test, hydro test, or whatever to confirm that your expansion is intact. Then you can apply the welding. This is one feature. But if you think on the opposite side, welding first, then expansion. Welding first means after doing the welding, maybe during the application of the expansion, you might cause some cracking to the weld itself. And we'll have some example also in the case histories where the weld applied and the expansion, and there is some contribution for affecting the leak because of this application. That's why in the standards there is some recommendation to maintain a gap between the expanded part and expanded part of the tube and the weld. You should have leave some gap or clearance, not expanded, to avoid impacting the weld. And there will be no chance to do tightness check for the expansion because welding already will do the sealing. So after doing the expansion later, you don't have any standalone inspection technique or leak test to confirm that your expansion applied correctly. One aspect you might need to think about in the expanded and seal welded joints. In expanded and seal welding joint, the main sealing here will be the expansion, and the seal weld is the supplement. Means you need to think about how to maintain your main seal in higher quality. So if you are thinking about compromising one of them, so in this case you need to think about maintaining the expansion rather than maintaining the seal weld. Yes, definitely you have to maintain both, but this is just a point to think about. The seal here, the expansion here is the main seal. In the strength weld plus light expansion, it is the opposite. Here the strength weld is the main sealing between the two sides, tube side and shield side. You have to think very carefully about maintaining the strength weld and over than the expansion. For the application of the cladding or weld overlay tube sheet, it is required to apply the cladding to the tube sheet in many situations, like having the corrosion resistance of the tube sheet face in case you have a corrosive media, and instead of having solid the tube sheet from higher material or high corrosion resistance alloy. to reduce the cost or maybe also the fabrication requirements. So only weld overlay or cladding surface will be applied here. In some other cases, also to avoid the similar weld between the tube and the tube sheet. So if you have the matching material from the cladding layer or weld overlay layer with the tube, so you'll avoid the issue of the similar weld, which can cause some cracking under thermal expansion, or also to avoid the galvanic corrosion. In some cases, we are applying the weld overlay so that in future, whenever we need to apply plugging here and the plug need to be welded to the face of the tube sheet, you will not require heat treatment. So if the base metal, for example, is chromium wool steel, and here if you applied some grade of austenitic stainless steel or nickel alloy, so in future if you need to plug, you can plug easily without and weld to the tube sheet face without the need of applied again post-weld heat treatment. We will notice something here for the recommended cladded thickness. Recommended cladded thickness, in case we have to expand only tube to tube sheet joint, the clad thickness here usually should be higher compared to the requirements of the, in case you have weld. Why? Because in case you need to do sealing by the expansion, you should have enough distance sealing between the alloy of the material of the tube and the alloyed part cladded here. Otherwise, if it is small expanded part, means you'll have higher chance to escape of the media to the lower grade material, which might be affected by the corrosion. But in the welding, the sealing will be by the welding to the clad here, so you don't need much higher thickness here. You need only thickness to respect the corrosion resistance, the dilution in the maybe first or second passes between the clad material or weld overlay and the tube sheet. That's all. We will see the same is applied in the two standards, in API 660 and TEMA standard as well. In API, they are asking for 10 mm tube sheet thickness in case you have the expanded, and 5 mm in case you have welded. In TEMA, the same approach but different values. They are recommended 7.8 mm for the expansion and 3.2 mm only in case you have weld. And there is 3 different techniques known in the market for the application of the cladding or the weld overlay: explosion welding, hot roll bond, and weld overlay. If you have hydrogen service, you have to be very careful about selection of the type of the weld overlay or the cladding. Hot roll somehow is the one of the least bonding between the cladding layer and the tube sheet base metal. That's why it is highly not advised or recommended for the hydrogen service. And in opposite, you can apply the weld overlay or maybe also the explosion welding, which has some acceptable bonding compared to the hot roll, which is not recommended for hydrogen service. One of the main features you have to respect and do it in high quality and properly is the understanding for the mock-up of the tube to tube sheet, especially for the welding application. We will see in ASME boiler and pressure vessel code section 9 in 193, QW 193, the recommendation for the application of the mock-up. Each welding procedure should have a mock-up, and also each welder qualification you should have a mock-up. For the welder qualification, you should have a mock-up with minimum 5 tubes, and for the mock-up for the procedure qualification, you should have minimum 10 tubes. And the material should match the material which will be used in the production. And whatever the testing required, and we will see in the next slide by the ASME, you need to think it about carefully. And if you have some special requirements for the service, you need to respect like the hardness, for example, for sour service application. One thing you need to think about while selecting the material for the mock-up for the tube sheet, in many cases they are using tube sheet from similar material, not exactly the material used in the application or the production. This is somehow might do some misleading results, especially if you have an improper properties or quality of the heat affected zone in the tube sheet side. If you have in the mock-up the tube sheet side weld The heat affected zone have some higher hardness, some issues, whatever in the microstructure, the grain size. If you are not using the same material for the production, you cannot rely on the results. You will not be able to reject it. And also from the other side, it will mask you from the results. It will not give you representative results. And we will see one example in the case histories for that. You will apply for some material, the result there will not be highly representative to your actual production, and you might end up by a failure because of that. For the mock-up procedure, here some recommended procedure for the mock-up. First, you need to be careful before applying the mock-up that you should have a detailed procedure what should be applied. Here we are providing some suggested or recommended step-by-step procedure for the application of the mock-up. First, you have to check the condition of the tube sheet hole and the tube surface. Measure and record the actual hole diameters of the tubes, inner diameter, tube thickness of all tubes, and for the hole as well, and this have to be well recorded and marked. Then follow the sequence of the expansion and the welding as agreed in the production. We said that you might do expansion first, then welding, or whatever agreed, you have to apply. Then do the visual examination. You have to see complete fusion, free of visual cracks, porosity indications. There is no evidence of tube burn through. And then apply liquid penetrant, and it is highly advised to apply for the root pass and again for the final pass. You need to measure and record the actual tube ID after the expansion to calculate how much reduction. This is for sure for the expansion cases. And then do the macro expansion. And while doing the macro expansion, ASME here is recommending magnification 10x to 20x, but actually it is highly preferred to be 20x or maybe even 25x to have a well representation for whatever lack of fusion or any porosity or lack of penetration. The quality of the weld joint is highly crucial for the long lasting and lifetime of the heat exchanger. And then you need to calculate and see how much the minimum leak path, and you need to have sure that there is no evidence for cracking and it has complete fusion. This is how the methods for how to measure the internal tube bore, and this equation from TIMA, how to calculate the measured or the expansion ratio. And this is an example for some of the calculation. We measured everything, tube sheet hole, tube OD, tube ID after expansion, and tube thickness. And those measures, as we said, should be the actual tube and hole dimensions measured during the mock-up, not something from the drawings or from the recorded value. Because if you can see here, 0.2 something from mm will have an impact on the calculated expansion ratio. Then you need to calculate the expansion ratio and compare it with the recommended value, how it should be. Now for the minimum leak path. Minimum leak path is the minimum path where the media can leak, and it can be defined as the minimum distance in any direction from the root of the TTS well to the nearest surface. As you can see here in this photo, you can see that it is the radius of the largest circle, which can be totally inscribed inside the weld, and whose center is the weld root. So you might in the drawing have some circles, should be the greatest one, which is fully enclosed. So the radius of this one will be the minimum leak path. Minimum leak path depend for sure on the configuration of the joint, whether it is fillet, grooved, or fillet plus groove, and also the actual shape of the application during the mock-up. Some concavity, convex, the actual geometry used, like that. If you see here the recommendation between API 660 and ASME section 9. In API 660, they are mentioning like the minimum leak path shall be as minimum 2/3 of the nominal tube thickness. In ASME section 9, they are saying that it should meet the required design, but there is no specific requirements how to calculate or how to measure. We will see in the next slide how to think about that. First, if you see the different configuration here and just think about what might be the minimum leak path. If you are saying from the design perspective during the design itself, in this type of joint, the fillet one, this will be the minimum leak path, the throat. This will be the minimum leak path. And for the groove, this will be the minimum leak path. But for the combined groove and fillet weld, so you need to combine both. The minimum leak path here will be this dimension plus the throat dimension, or like that. So from this, we will see in the next slide our example. If we will respect the design to meet the requirement of the design as section 9 said, we'll see how to apply this in our test. We will assume here an example just for illustration. A tube of carbon steel, 179 carbon steel, welded to a tube sheet 266 grade 2, all carbon steel. Tube diameter is 3/4 inch, and BWG 14, which is 2.108 mm. Design temperature is 200 degrees Celsius. We assume this to build these two examples, one for fillet weld and one for groove weld. The same equation, if you can remember from UW20, here we will use for calculating how much AR is required. And from the AR, we calculated, we get the allowable stress from section 2 part D for the tube and for the tube sheet, and then get FWFD, which will be used in this equation. And here, if you can see the AR calculated, the result is 2.93 against the tube thickness 2.108. So it is higher than the tube thickness. And as per the recommendation for the fillet, AF, this one, should be the minimum of 1.40 or the AR. So it will be here 1.40 is 2.825. So AR is higher than 1.40. So AF will be 2.93 like the AR. The minimum leak path here from the design perspective, it will be this, the throat. So if we calculated the throat will be AF over square root of 2. So it will be 2.07. So from this calculation, if we respect to meet the design code, this is the minimum leak path for the design configuration. So in this case, MLB is 2.07 mm. If we check as per API 660, the 2/3 of the thickness is 1.405. So here from the method we are following in this calculation, it is much more stringent and conservative compared to the 2/3 of API 660. For the same example, we calculated for the only groove, and for the groove, the same equation of the AR here, but here the AF should be the minimum, or the AG should be the minimum of T or the AR. So in this case, it will be 2.93, same. And the calculated minimum leak path will be 2.93 because this will be the side of the weld joint of the groove. So it is the same like the AG. While we are calculating as per to API 660, 1.405. So here also is much more conservative compared to API, and also compared to the required for the fillet weld. This is one approach to think about the minimum leak path, which should be checked in the mockup. Now this section will talk about the common defects which you can see in the tube to tube sheet joint. This figure shows how the most common defects in the tube as a whole part in the tube sheet, and we will focus here mainly on the area of the tube to tube sheet joint, where we can see maybe you have galvanic corrosion, where we have inlet erosion. It might be in the first part of the tube, and also might be in the face in the tube to tube sheet joint. We might have stress corrosion cracking, and the crevice corrosion from the shell side also might affect the joint. As a general thinking, corrosion might happen by the combination of environment, material, and stress. Environment, stress, and the material together, if the condition can be applied for stress corrosion cracking to have the three required factors. And environment with stress only, you might have corrosion fatigue. Material with susceptible environment with susceptible material, you might have corrosion, and the material with distresses, you might have fatigue. The most common for the tube to tube sheet joint, first we will start by the crevice corrosion, and here there is an example of crevice corrosion from the back side of the tube, where you can see the full tube thickness has gone, and you can see the leak directly there. And the crevice corrosion, as per this curve we get from NALCO guide to the cooling water system, you'll have there is some incubation period for the crevice corrosion, and after some time which usually in many cases it will have might be 1 year more or less, then you will have some exponential acceleration rate for the corrosion attack. To close the crevice or to eliminate this crevice corrosion, you need to think about the proper expansion of the tube to tube sheet so that you can close the crevice, or you might think about using the setback weld to expansion or setback weld, or you might think about the internal bore if applicable or if can be applied. And you might select about more resistant material, so the condition is there but the material somehow will higher resistance, or to maintain the condition of the fluid itself to somehow reduce the tendency to cause the corrosion. And in some designs in the heat exchanger itself, you might have such kind of vapor bleeding to avoid the stagnation of the tapped vapors like that. For the pitting also attack, you can see in the tube-to-tube sheet joint here, and there is some, you can think about the having resistance material with higher pitting resistance equivalent number, or to avoid stagnation, it is highly recommended to have the tubes flushed with the tube sheet, especially for the vertical heat exchangers, to avoid such deposition or accumulation, which might cause the pitting and corrosion in the top face, including the tube-to-tube sheet joint. And you need to maintain the protective film of the material. In many cases, in some services, you might have intentionally adding some oxidized material to maintain the passivity, like in some boiler filter system, in some application of the carbamate in urea plants, like that. And avoid condensate corrosion, so maintain the temperature higher than the dew point, like the case of the CO2 services. Erosion corrosion, this photo, if you can see, there is some high erosion to the face of the tube sheet, including the tube to tube sheet joint and the inlet or the first part of the tube itself. So by the time this might have a corrosion or might have the metal loss leading to a leak here. So you might think about changing the configuration of the geometry to avoid such high impact of the erosion, or maybe utilizing impingement protection in the channel itself somehow, some perforation, something like that, to protect the tube from the direct impingement, or to improve the resistance of the material by having higher hardness material. And in some designs you can have the ferrules here to protect the first part of the tube, including this flared end, which will protect the joint as well. For the stress corrosion cracking, as we said, the material, environment, and the stresses all should be there to have stress corrosion cracking. It is one of the most common issues in this tube-to-tube sheet joint to have such kind of cracking. So in this one, it's all somehow, in many cases, linked with the crevice corrosion. In case you have crevice here, you might have the attack on the weld by stress corrosion cracking. And to avoid that and control it, you might need to use higher resistant material. You need to avoid the residual stresses, and by avoiding the residual stresses here, you need to think about the way you are applied the weld, and also the expansion, the ratio of the expansion you have applied, and also to have a clearance between the expanded part and the tube and the weld. Don't apply the expansion up to the weld or with minor clearance to the weld, so you'll have higher residual stresses or stress concentration part in this area. And apply the proper expansion. Full weld penetration is highly crucial in avoiding that. Otherwise, the root pass will be an initiation part. It might be considered like a crack initiation in many cases of the stress corrosion cracking services. And also from the service perspective or the design of the heat exchanger itself, you need to reduce the bundle vibration or cyclic services. Otherwise, the tube, when it is vibrating like that, all of these stresses from the vibration will be converted directly to the weld joint and leading to cracking or stress corrosion cracking. Those are one of the table for the most common services causing stress corrosion cracking in some of the material. After the session, we will share this material in PDF format with all attendees, and this table reference from the NALCO guide to cooling water system. For the galvanic corrosion, you can see here you can see the preferential attack of the tube-to-tube sheet joint in some galvanic corrosion, and it is not something uncommon. You can see this in the industry, and somehow you need to think about, as we mentioned earlier, you might apply the cladding to avoid the dissimilar metal here, so you will not have the differential in the potential which causes galvanic corrosion. And in some cases you might apply there is some special coatings like the epoxy coating which might apply to the face of the tube sheet, and also including the tubes. In many applications it is applied, and this will have some good effect on eliminating or mitigating the galvanic corrosion. Here some summary for the most common weld issues we can see in the tube to tube sheet joint. The porosity, which might be by insufficient shielding or purging gas, or maybe the unclean base material, unclean filler, and you have to use sufficient flow of shielding or purging or proper cleaning of the before the application of the weld itself, and the base metal and the filler wire as well. Lack of fusion, improper welding parameters, low current, high speed, and this might be the causes. And this is one of the famous issues in the tube-to-tube sheet joint, both of them, the lack of fusion and the incomplete penetration. Incomplete penetration, whether by controlling the weld parameters itself or from the design perspective to have proper groove size or groove shape, so that you can have better chance to apply good penetration for the weld itself. And also from the selection of the filler wire size to have smaller one, so you might have also proper penetration during the application of the root pass. Burn through somehow you can see in thin tubes in some applications, and you need to control the heat input to avoid that. Undercut, and this is one of the high current or maybe long arc length, and use the proper welding technique and parameters. And that's why the mock-up, if you are fixing for the qualification of the WPS by the mock-up, you can fix all the parameters like that. And also you might have the cracking in the tube-to-tube sheet joint, whether from the you can see the high restrained or unclean surface. And here you need to think about, as you said earlier, the high heat sink you can see from the thick tube sheet. You need to think about the proper control of the heat input and heat dissipation during the application of the weld. Those are the most common inspection techniques we are using for the tube-to-tube sheet joint, whether after or during the fabrication, or in service inspection, or during the repair activity. The visual examination, surface examination by DBT, volumetric examination by UT. Somehow this technique is limited to some configuration and it's not commonly used. In situ replica, a replica can be applied, but also it is challenging because the tube, the weld itself, somehow you might not have enough landing space or area to apply the replica. And the helium leak test, hydrostatic leak test, and you might see the for the erosion or the during the service or the expansion, how much actual tube ID using the calipers like what you can see here. Radiographic examination, RT, and somehow this is a recent technique. It's not something common in the industry. Still, we can see some manufacturers talking about that, but still not commonly used in the industry. Now, this section will talk about the leak repair. Whenever you have a leak, you might think about whether TTS weld repair or re-expanding again, or might be retubing or plugging. And in plugging, you might have taper plug, mechanical plug, or welded plug, or applying internal sleeve or ferrule to protect the tube. Here this is a recommended or suggested procedure for the weld repair. First, you need to grind out the affected part, and this shall be done very carefully because especially in case you have some crack or something during the grind out, the crack might propagate. This is a risky application, so it's prefer to have a pencil grinder with carefully application, although it is a time consuming. Then apply stepwise DBT to confirm that the full defect is already removed. Then apply the welding first pass. Do DBT for this pass. You might apply pre-leak test after the first pass apply to confirm its intact and integrity. Then apply the second and the filling passes. DBT again. If post-welding treatment, you need to apply it. And it is something challenging. Application of the post-welding treatment inside for the tube sheet is not an easy application to confirm the uniform and proper heat distribution and the application. It shall be carefully applied, and in some cases you might need to do finite element analysis to confirm that thermal and mechanical stresses during the application are within the accepted values, which will not harm the equipment. And if you apply this one, you need to do the expanding again, do the hardness test, ferrite content if applicable, and the final hydro test and helium leak test if critical service required helium leak test for during the preparation you might do the mock-up, especially for critical equipment, before trying to do any repair. For the plugging, we said we have many types of plugs. This is the most common one, the plug or the most simple one, the tapered plug. Tapered plug to be used, if we can see here from ASME PCC2, it is somehow limited to a little bit lower pressure and temperature, and also in case the tube-to-tube sheet joint is not welded. During the application of the plug, it is recommended to pierce the tube before. Here we are talking about plugging tubes with thickness loss, but it's not leaking. If it's leaking, no issue. But if it's not leaking, means you need to apply some piercing of the tube, because if you apply plug like that, then some media will be trapped in the tube, and during service and heating, it will create some vapor pressure. Increasing the pressure might cause the plug to fly like that, and it might cause an incident. So it's highly recommended to pierce the tube as per PCC2. Two holes need to be applied before applying the plug. Plugging means you are restricting the flow, so you will might impact the pressure drop and the thermal performance of the equipment itself. And later, when we see the mechanical plug, even the integrity by applying the welded plug, the integrity itself might be impacted. This mechanical plug somehow is recommended or can be used for higher pressure application. If you can see here from this illustrative graphics how it is applied, it is inserted. Then by hydraulic machine, the inner part is somehow pulled like that, and while pulling here, and this is covered, it is like a labyrinth. This labyrinth will be sealed against the tube and force the tube also to seal against the tube sheet. Mechanical plugs, you might apply many shapes of the mechanical plugs based on the design, the configuration, limitation at site, like that. We can see here that some shapes of the mechanical plugs where you can weld to the outer surface of the tube sheet, inner surface of the tube, applying over the tube itself like that, or like this somehow similar, or even cut part of the tube and insert it, or insert it inside the tube and weld to the tube, similar to this. Welding, you need to think about the application of the welding here. Mock-up is highly advised to be applied or prepared before the application, especially for the qualification of the welders. In some cases, just starting to attend some leaking part by welding, you might create issues for the other adjacent tube. So this application shall be done with high care. Now this is our last part. We will see some case history showing some good cases like this one. This with internal bore weld, and this internal bore weld, if you can see in this photo, it was leaking from the weld itself. The service is in hydrogen service, and there is a weld overlay here, but welding between the tube and the tube sheet, as you can see in this configuration. This one was repaired at site, where they installed some ferrule inside the tube and welded to the tube inner surface from here and the tube sheet surface from the outer side. They have made many mock-up until have good confidence in the applied technique. During the investigation, they have taken sample from the failed tube, and in this sample, the conclusion that actually it was in service for short time, and they found that it is related to improper application of the initial mock-up of the during the equipment fabrication. They used the tube sheet material, a similar material, but not from the same heat number, And when they used now the sample from the actual failed tube sheet, they found the coarse grain and high hardness and some impurity material in the tube sheet. So somehow during the mockup, if they are using the same part from the or part from the production material itself, you will have a representative results and avoid such issue. This is the second case. This second case, it was a waste heat boiler in ammonia plant, and cracks found in many parts, including the tube-to-tube sheet joints. The tube material is austenitic stainless steel, and the cracks are stress corrosion cracking from the boiler feed water side from the shell side. And it is due to the improper expansion of the tube to tube sheet. That's why you are saying the proper expansion to avoid the crevice corrosion is highly crucial to the equipment in many cases, especially whenever you have material susceptible to stress corrosion cracking. This is another interesting case. This is a high pressure carbamate condenser. Some pinhole in the one of the TTS minor one, causing the carbamate from the tube side to pass in the to the shell side. And if you can see here this photo after removing this part, this photo, there is a very big cavity in the tube sheet, carbon steel tube sheet. And this was in short time because the carbamate is highly aggressive media. And that's why there is no one, as we said, there is no one solution fits all. In the previous case history, we said crevice corrosion shall be closed by proper expansion. It is highly crucial. You have to follow this. But in this case, it is highly recommended not to do expansion and leave a clearance or a gap between the tube and the tube sheet hole, so that in case some leaks like that, it will pass easily to the tube sheet, to the shell side. And once passed to the shell side, there is some online monitoring for the parameters of the water here. So the conductivity will increase sharply, ammonia will be detected. So you might have the good time to attend the equipment before having such massive impact on the equipment. So as we said in our initial slide, balance your choice for the selection of the material. This is another case history for a heat exchanger, and it was in service for very short time, only 30 days in service. After 30 days in service, cracks initiated exactly beside the root of the tube-to-tube sheet joint. It is austenitic stainless steel, welded and expanded. And during the investigation, they found that there is some lack of fusion in the weld, and also the expansion is extended up to the weld joint. That causes stress concentration, which they confirmed its impact by finite element analysis. And somehow in very short time means there is definitely some contribution from cyclic service or vibration in the bundle itself causing this attack. That's why the weld quality is very crucial. Inspection techniques somehow are limited, especially for the weld pass. So mock-up is very important to ensure the quality of the joint. And also you should have enough clearance between the tube and the tube sheet, so that enough clearance between the expanded part and the weld of the tube to tube sheet, so that you will not affect the weld by cracking or having high residual stresses or in this or stress concentration in this area. And also based on the service, you have to mitigate the vibration, and this is mainly part of the thermal and performance design. By that, we have come to our suggested reading to go for maybe TEMA, API 660, ASME boiler under pressure vessel code, NALCO guide for cooling water system, ASME BCC2, and the API technical report 938 for the duplex stainless steel. Now we came to the end of our presentation, and Dr. Krishnan, please, you might go for the discussion. Hello?
Dr. Krishnan? Hello?
Yeah. Hello, Dr. Krishnan?
Dr. Krishnan?
Hello.
Yeah.
Let me check.